Tonight is December the 14th, 2019. I'm going to make some ongoing videos on these power supplies and modulator that I'm building, rather than try to make one that's 2 hours long and all-encompassing. And there seems to be reasonable interest in these mercury vapor rectifiers and power supplies. It's something that I've done so much of, I don't give it much thought sometimes. I build these things out of my head. This one is a full wave. It's got the two diodes. These are the anodes, of course, and it's hooked up in this case just like if it were a full wave center tap. But I'm not using the center tap over here. I'm using another stack of solid state diodes for the other half of the bridge. So in this case, you hook the output of the transformer to the anodes here of these tubes. I'm using these tubes just because I like them. And then the solid state rectifiers, you hook the cathodes to the same point on the transformer, and you ground the anode. That gives you the negative cycle rectified. This gives you the positive cycle rectified. I did have to change this transformer out. The other one was so old it just quit. You know, it was going to blow up on me. Actually, already did. But anyway, that's what it is. I've got way too much capacitance. I realize that, quite honestly. I've got 470 microfarads times 6. And then I got another 470 microfarads, 6 of them in series. So if you do the math, you get 470 microfarads. That's actually divided by 3. You get 156 microfarads. Get the glare off of it there. That's really way too much. These kind of power supplies, 10 microfarads out there is usually enough. But I think I'm going to leave it that way. The reason I did it like this is I wanted to have the option with this with these electrolytics to change this to a voltage doubler if I ever want to. If I change it to a voltage doubler, I would not need this stack back here. I could use these two, but I'd need another filament transformer. And then I could make it a voltage doubler, and then I'd end up with, well, twice what we're going to get here. You'll see in a minute. We'll end up with twice that. But that's not loaded. So under load, it'll drop down to about 4,000. And this one will drop down to about 2,000. I think about 2,200 is what it'll drop to. And if it was in a doubler, it'd be up around 4,000, but I don't need 4,000 right now. This is a filament transformer. It's a 5 volt 30 amp. I get them from Hammond. I buy them from RF Parts, I believe. They're a good seller. Well, let me show you what this thing does. It's actually working wise complete. Oh, this was something a gentleman asked me about today. Do I use high voltage fuses? And the answer is no, I don't have any. But here's what I use for a high voltage fuse. I gotta move the camera a little bit and kind of zoom in. And this has worked very well for me. I use these little fractional ohm resistors in series with the output. This one happens right here, happens to be a 0.33. I think you can see it right there. I want to touch it with something. The power supply is off, but still, I'm going to touch it with a pencil. I know I've been warned about the carbon too, but it is off. I just took the ground wire off here. This 0.33 ohm resistor, it can be a 0.47, it can be a 1 ohm, just something small, and it's a 1 watt. And this is coming straight out of the power supply. This is going to that milling connector here in the back. I can't show you the whole thing right now. Well, actually, maybe I can. I'll show you what I use on the output. I use these type of high voltage connectors right here. Hope I'm getting the camera properly. Where's the camera? There it is. I'm sorry, I got to zoom out here. I'm zoomed in way too close. Let me get all the way back out. We use these little types of high voltage connectors. This goes into the chassis. The wire goes into here. I personally use this this red. high voltage meter lead. This is the type, I got lucky, this is the type that does not have that string inside. Some of them have a string inside that, you know, just to make it stronger, like if you're going to use it for meter lead. This one doesn't, so it makes it a whole lot easier. Otherwise, you're always trying to trim that darn string off. But those are the kind of connectors I use. I use actually this same kind of wire between them. I also put a metal stud, a metal screw like an 832 or a 1032 on the back. And I make sure I've got a ground strap between chassis too. Because you don't want these things to come ungrounded from one another, because then you could develop high voltage between them, and if you get between them, well, then you're going to be the return, and it's probably going to kill you. So that's what I use for high voltage. I've been using them for many years. I did have one go bad not too long ago. It was probably cracked. Maybe I tightened down the little mounting screws too hard or something, I don't know, and when it arced, it just exploded. Just blew it all over the room. I showed that on an earlier video. Okay, well, let's turn it on, and I'll show you what kind of voltage you get, and I'll show you something that I use to measure voltage if I have to do it very carefully, or very accurately. But you know what, excuse me, one more thing though before we get there. How do you turn this thing on and off? Well, again, since I use all vintage boat anchor stuff, this stuff is pretty natural to me, but not everybody does it like this anymore. You know, in your transmitter or your transceiver, or your exciter, whatever you want to call it. Most oftentimes you do have a TR relay, a transmit receive relay, so that when you squeeze the microphone and you put your rig into transmit, it closes a relay. Now, the old ones used actual relay contacts, and you could just do just about anything you wanted to them. The modern day ones do not use physical metal contacting relays. They use a little solid state circuit, and you have to be very careful with them or you're going to bust it. And what I do on my little ICOM transceiver is I use the internal solid state TR switching inside to actuate a real genuine outboard physical relay. And that way I can put 110 volts across the contacts if I want to. I don't do that, but 12 volts or 24 volts, I don't have to worry about polarity. It's just a relay contact, and here's what I do right here. I'm going to move the camera around here and scope in on this, and I'll show you exactly how I do it. Hope all this is get the glare off of it. The darn glare is always the problem. Yeah, I think you can see that pretty good. I built this into just a relay box, or I mean a little chassis box of some sort. And in my case, I use 24 volts, and I use 24 volt relays out here. You could use 12 and 12, whatever you happen to have or whatever you happen to like. But these are little pre-assembled 24 volt power supplies I was lucky enough to run across. I just used them. Of course, you could use a 12 or 24 volt transformer. You know how to build all this stuff into a bridge or whatever. Anyway, you put it through to one side of your relay, and the other side goes out to your TR switch. This is actually going to go out to your transceiver or your exciter, so that when you key your transmitter, it's going to actuate this relay. And then you set up all these contacts inside. You can set them up for normally open or normally closed, whatever you need. Well, in most of the cases that I have, I think my R390 needs an open contact to mute. In most of the cases, what I use is a closed contact to actuate my power supplies. So I would use the common and the normally open. I put them in a little RCA connector, so I can put all this stuff together, an RCA connector from here to the other, to the power supplies or whatever. I've got an RCA connector on the back of this one. So like I say, this one is for all practical purposes complete. So what we want to do is turn it on. I'll show you how I measure it. I'll show you what it does. I know you've seen it turned on before, but let me turn it around here and show you how I use a digital voltmeter on it to measure 2500 volts. Okay, this one right here, we got to scoot back out. I'm using an old triplet 630 over here, marvelous meter. Got to have one of these if you're going to play with high voltage. Some of them do 5,000 volts, some of them do 6,000. This model happens to do 6,000. You got to move your probes around. Common here, 6,000 volt DC, and it works. Now, what I do here is, of course, this switch right here just simply turns it on, let the filaments warm up. I don't have any time delay relays in there. I just gotta give it some reasonable time. And when I turn this one on, you see the red light come on. Let's scoot it back down. Let's move the camera back again. I know some of y'all hate me moving the camera around, but I just don't seem to have many other options. And what I was just talking about is I use RCA type connectors and what have you. RCA connector here. Plug it into the back. I've got this end cut off of this particular one so I can use it. I'm going to plug it in back there. And now that I've got that this switch up, when this would be like, this is going to actually plug into that little box I just showed you, and when I key the transmitter and that relay in there energizes, it closes this contact and it comes on. And when I let go of the microphone, it goes off. Key the microphone, turn on. Oh no, got to be very careful here. I'm going to disable this right now. When I disable that, that's on purpose. See, this doesn't do anything, so I have it fixed so that I can disable it. Now the voltage, let's look at the voltage. It's actually pretty severe. Excuse me, got to go back and forth. But I'm going to show you how I use my digital voltmeter on this here in just a second. Keep my left hand in my pocket. Work with one hand. You got to do that if you want to stay alive. Let's hook this guy up. And without a whole lot to do here, it actually comes up to on the 6,000 volt scale. You should be able to see this. I have to do this very carefully because it's actually pretty distracting making these movies and messing with stuff at the same time. You can see it's still up at over 1,500 volts right here. That's because my bleeder resistors are actually very high resistance. But let's turn it back on, and then I'll actuate it again. See, it's jumping up to 2,500 volts, if you could read that. That's a little high for what I want, but this is with no load. I figure it'll load down to, that's maybe about 2,600. I can't get down real close to it. Actually, I can see it better at the camera once the video is posted than I can here standing in the room. I'm going to turn it off. See, it bleeds down pretty slow. I may do something about that. I was thinking about putting another relay with maybe like a 50K resistor across it, so that when I turn it off, that relay closes with that 50K resistor and bleeds it off pretty quick. Because I don't want that resistor on it the whole time that the power supply is on, because it just dissipates a whole lot of heat. You know, just draws a lot of current and makes a lot of heat. So I'm just thinking about doing that. I'll probably need a high voltage relay. Well, I got that too, so I got plenty of that kind of stuff. Let me show you how I use my my Fluke and Tektronix meters on this. These meters say, if you look at them carefully, 1,000 volts DC. I do not recommend putting 1,000 volts on this thing. It's probably not going to be good for it. 1,000 volts DC or 750 volts AC, because you know the peak on AC is a whole lot higher. It's peak to peak's 2.828 times, 2 times the square root of 2, and just the peak is the square root of 2 times the RMS. Anyway, let's hook this guy up. I don't you be able to see it. and I've been lucky enough to come across one of these guys. It's a times 100 probe, and I have checked it out, and it's amazingly accurate. It's accurate to about 1%. The meters are accurate to about 0.01%, but 1% is darn good. This thing is extremely good. It's got a it tells you right here it's times 100, and it says it has a well, it says 10 meg ohm inputs. It doesn't say it's for DC only, but it is for DC only. I hear my kitty cat out there. She can wait a minute. Okay, so we'll hook this guy up, get a ground. Got to remember there's still some voltage on this, but we'll hook the ground up right there, and we'll actuate it again. We'll turn it back on. I think what I'll do is just twist these two together, just like I was actuating it all the time. I don't want my kitty cat in here while I'm doing this. And then I'll turn this on, and that will power it up. There you go. And then we can, I'm not going to hold both of them. I will not use both hands. I need to set this so we can read it. And I'll show you how accurate these things are. It's pretty amazing. And then with my left hand in my pocket, I'm going to reach over here and touch the high voltage with this guy. Am I doing everything right? There you go. See, it says it's 25.15. That's times 100. So that's 2,500 volts. So that would be 2,536. 2,550. I guess it's soaring a little bit because there's no load on it, so it's going to end up with line fluctuations and everything. You know, it's going to be multiplied. Whatever the line fluctuations are, it's going to be multiplied out here. It's all the way up to 2,570. And if I look at this one says it's closest I can read, says it's 2,600, 2,600. So they're only different by about 30 volts. So it's pretty good. So you might want to get one of these. Always keeping your left hand in your pocket. Never touching anything with both hands. I'm going to turn it off. And, well, actually we can leave this hooked up, and you'll see it actually dies down pretty slow. It's down to 2,350, 30. Yeah, a relay with the contacts open while the amplifier is on, with a 50K or 100K resistor in series with it across the high voltage supply, meaning that when you turn the power supply off, when you let go of the transmit receive relay, it would place that across there, and I think that'd make it a whole lot safer. It would probably bleed down in just a few seconds. So I may do that because you can see it's still up to 1,800 volts. So there you go. Let me think about something else here, because I always, when I make these little short videos, there's always things that I wish I had brought into and mentioned. Well, I will show you how I discharge these things in a reasonable manner. I like to use, this is a 1,000 ohm resistor. I'm going to hook it up to the ground. I'm going to hook it up to, here it is right here. It's just a 1,000 ohm, kind of a big resistor. Let's zoom back out all the way. 1,000 ohm resistor. And always, when we get to the high voltage, one hand in our pocket behind us, not going to touch anything. Sorry for the fumbling, but I got to be careful here. I've got it hooked to ground right now, so I'm not. Ambulance is going everywhere. Holy cow! And when I touch it up here, it'll probably let out a little bit of a. No, not much. And just with a 1K resistor, see, it went to. If you could read the meter here again, it went to virtually zero. And there was no big bang or anything. You really don't want to charge these capacitors up 150 microfarads to 2500 volts and dead short them. That's a bad idea. Back in 1970 when I first started, I remember I had a big capacitor one. I was poor back then, you know. I didn't have all the money to spend on capacitors and relays and what have you. And I had a 4 microfarad 4000 volt capacitor, and I remember it was in an 813 amplifier. I didn't have any bleeder resistors on it, and I was working on it, and I knew it had charged up. And I said, well, what am I going to do? I got to discharge this thing. I knew not to touch it or it'd kill me. So I just squatted down behind it with a jumper lead and hooked one lead to ground, and I stuck the other one against that screw coming out of the ceramic insulator, and wow, that was like firing a 45 in my face. It was so damn loud, my ears were ringing. It was just god-awful flash, and that was 4 microfarads, but it was at 4000 volts too. So don't just dead short these things. That's a really bad idea. You know, you got to stay safe. These things are just beautiful. We all seem to love these mercury vapor rectifiers for some reason. They're actually quite nice, you know. They're very powerful. They have 10 to 15 volts drop across them constant. Extremely high voltage. They just are the cat's meow for such a old technology. These right here are dated somewhere between 1941 and 1945. These are truly World War II mercury vapor rectifiers right here. Okay. Stay safe, my friend. Have fun. Okay, well, while we're at it tonight, I think I'll go ahead and give you a simplified diagram of an AM transmitter. There seems to be quite a bit of interest in it. Building an AM transmitter from a blank chassis up, it's a lot of work. I forgot how much work it was. Of course, I did this when I was 50 years younger, first time. But I'm really enjoying it this time. It's just the stuff is so damned heavy. But anyway, an AM transmitter is actually fairly simple. I'll make it as quick as I can. This is your modulator. It's an audio amplifier, just like the amplifiers that you see me make and you guys make all the time. The only difference is it doesn't have an 8 ohm output. It has an output. It has a secondary winding that's equal, that matches the plate load impedance of your Class C amplifier tube. This has to be Class C to plate modulate it, which is usually in the 3000 ohm range. That's just a reasonable value. So it's a big amplifier. If this is a 1000 watt RF amplifier, to modulate it completely, this has to be a 500 watt audio amplifier. Modulator, audio amplifier, same difference. Of course, then the modulator here doesn't have to go from 20 hertz to 20 kilohertz. The voice range is generally from like 300 hertz to 3 kilohertz. So it doesn't have to be anything real fancy. But it does have a very special transformer here, very special high voltage modulation transformer because of the the secondary impedance. Okay, now this being the RF tube, this is a big plate choke that's in all of them, and normally this goes to the B+. But instead of going straight to the B+, we do it like this. We connect it over to this transformer, and then we send this to the B+. That's 99% it. Now, you know, to make better ones, they put some extra little windings on here, like to modulate the screen in case this is a tetrode. But this is it in its simplest form. Now, a Class C amplifier is a really interesting and unique design because the bias on it, you know, a Class A amplifier is biased so that plate current flows 360 degrees. You never even come close to shutting off plate current. Class C amplifier, let's jump to it. It is biased at twice its cutoff value. like if it takes 60 volts to cut it off so that there's no current flowing from the cathode to the plate, then you set it at like 120. These are not exact numbers, but this is the way it works. You set it for about twice the cutoff. So here's the beautiful thing about a Class C amplifier and a pi network that all of you may not know. If we draw the pi network here, the pi network is, you know, it's got two capacitors on it. These go to ground. The resonant circuit, by the way, is these two series capacitors across this L right here. 2 pi, 1 over 2 pi LC. But this right here, you know, is just an extension of over here. And what the way the Class C amplifier works, and the reason you can't use it for stereo, is what you're putting into it over here is just a pulse. That's all you're putting into it. Because remember, you got it biased off really, really hard. You're missing this part right here. You never even put that in. Then the next cycle, you put another big pulse into it. But the way a pi network works is when you put a big pulse into this pi network, it charges up the field around this coil. The capacitors charge up. And I don't know if you know this or not, but if you take a coil and you put, like, we'll draw you remember some of these things from your stuff, you put a battery across it. When you close this switch, this coil charges up with a big magnetic field around it, you know, just like I was drawing there a while ago. And if this is plus and if this is minus, right? But when you open this switch, the polarity reverses. This one was plus and minus when you charged it, but when you open that switch, this one became plus and this one became minus. It switches polarity on you. So the really amazing thing about a Class C amplifier and a pi network is when you charge it up with this big pulse right here, and then the two being biased off, when this big positive pulse goes away, you're not pumping any energy into this pi network anymore. This is your pi network. And when all of this magnetic field collapses, it adds this one back. So your tube is only working less than half the time. That's what makes them so efficient. They're 75% efficient. And this works just like this little magnet right here. You're charging it up plus to minus, and then when it shuts off right here and the polarity reverses, you get the minus to plus. Polarity reversal. And that's the way a Class C amplifier and a pi network operates. But this is, it's just, in a nutshell, just basically this simple. And you can run everything off of one power supply if you want to. You don't have to have a separate power supply for your audio amplifier and your Class C amplifier, assuming, you know, they're the same class tubes. If this were a big transistor amp, of course, you wouldn't use it at all. Now, what I'm going to do in my case is I've got these big transformers on the modulator, and they have lots and lots and lots of taps over here. Well, what I'm going to do is put another one over here just like it, and then I'm going to move these taps around. This is high Z, this is low Z, this is low Z, this is high Z. I've done this before, it works beautiful. These are two exactly the same transformers. So I'm converting high impedance back to high impedance. And the efficiency of a transformer is actually quite high, so the amount of energy I'm losing in there is very low. Well, anyway, in a nutshell, that's how an AM transmitter works, and the action of the pi network and the Class C bias and all that kind of stuff. So there you go. Hope that makes sense and helps.